Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Okay, we are discussing the question bank discussions. Question bank questions are important derivations also, mainly heat exchange between the two surfaces. So, surfaces are different types. We'll see. Question will be like this one. Derive the radiative heat exchange between the two gray surfaces. Those surfaces either very parallel plates or a small body in a large enclosure, and next to two infinite parallel planes also separated by very small distance, next to between two parallel plates with shield. So these are the four conditions we'll see. We'll derive the formulas. Next we'll see some numericals also. So this is the just like derivation which is given in the question bank. Now we'll see how to derive this formulas. First we'll see there are, in the previous class we already discussed that the radiation energy, suppose this is the surface, this is the incident radiation. So some portion will be reflected, some portion will be absorbed, some portion will be emitted. Okay, so rho g, this is the g, this one is the epsilon eb. So this one is a emitting energy. Okay, so the both of these one, that is called radiosity, z is equal to rho g plus epsilon eb. Okay, so you know this one radiosity. To derive this formula, that one is, it means rate of heat transfer in this surface we already derived in previous class, that is EB, emissive power, total emissive power minus radiosity by surface resistance 1 minus epsilon by epsilon. So this was derived in previous class. Okay, so 1 minus epsilon by epsilon, that shows the surface resistance. This surface resistance. EB is the emitting energy, that is the total emission energy or emitting energy. J is the radiosity. Radiosity is nothing but rho g plus EB. Okay, so every particular surface that has surface resistance and these are the total emissive power and radiosities also. Okay, so based upon this formula, we will derive the rate of heat transfer between the two surfaces. Okay, just here I am taking the two surfaces. The surface 1, this is the first surface. Okay, so this surface, it has the thermal resistance of this surface, you can write like this one. So for this one, EB to resistance to radiosity. Okay, so 1 minus epsilon 1 by, suppose this is the first surface, emissivity is equal to epsilon 1. Then if you consider area is equal to A1. Okay, so 1 minus epsilon 1 by epsilon 1. Then rate of heat transfer Q by A is equal to emitting energy differences EB minus J by 1 minus epsilon 1 by epsilon 1. Okay, so for this first surface, it starts with emitting energy EB1, then thermal resistances. This thermal resistance, surface thermal resistance, nothing but 1 minus epsilon 1 by epsilon 1. Okay, this is the area. Then it will become so J1, radiosity of the first plate. Okay, so similarly for the second surface, this one also, this is the EB2, emissive power B2, it will start, and surface resistance, that is the 1 minus epsilon 2 by epsilon 2, then it comes to J2. It means radiosity with respect to surface 2. This is surface 2, this is the surface 1, area epsilon 2, emissivity, temperature T2, this is the temperature T1. Okay, area is the just like A2. Hmm. So then we have to consider the one more resistance, that is called the resistance between the J1 and J2. Okay, radius it is between the plate 1 and plate 2. So that radius, that resistance is nothing but space resistance. Okay, this space resistance depend upon the area and shape factor or view factor also. So that is nothing but 1 by A1 F12. F1. It means heat transfer takes place from plate 1 to plate 2. Okay, so we are considering, it means F I to J. So we are taking this view factor with respect to from I to J. So heat transfer takes place from I surface to J surface, or heat transfer takes place from surface 1 to surface 2. So we are considering view factor F12. So area of the first plate. So we have to, this is nothing but this is the space resistance. Okay. So uh, if you want to calculate the rate of heat transfer between any two surfaces, you have to consider three resistances. Two are the surface resistance of first surface. Second one is the surface resistance of the second plate. Next, we'll see the space resistance between the two radiusities. Okay. So then the final formula, you know this one. This is the electrical analog formula. You know that the advantage of the electrical analog formula, you know, we already discussed in previous class. Okay, so this is the EB1. It will start first surface resistance 1 minus epsilon 1 by epsilon 1. If you consider area A1, 1 minus epsilon 1 by A1 epsilon 1. Okay, so next to J1. Similarly, from surface 2, this is the EB2, emissive power from the black body to next to surface resistance of the black body to 1 minus epsilon 2 by A2 into epsilon 2. Okay, so this one is the J2. So the resistance between the J1 and J2, so that is called space resistance. That is nothing but, so because heat is transferred from transmission or transferring from surface 1 to surface 2, then you have to consider area of the first surface and the view factor with respect to surface 1 to 2. F1 to F1 to or F22 or F2 don't take those things. Okay, so this is called space resistance. Then the final formula for the rate of heat transfer between the surface 1 to surface 2 by radiation process, that the formula is nothing but, so initial temperature or initial energy minus final energy, EB1 minus EB2 by total resistances. So there are three resistance. This is the resistance 1, this is the resistance 2, this is the resistance 3. Okay, so three resistance. So the final formula is equal to like this one. Okay, so by using this formula, you can understand rate of heat transfer between the two surfaces. Okay, so this is the general derivation for any two surfaces, radiation between the any two surfaces. Okay, so this is the formula: 1 minus epsilon 1 by A1 epsilon 1, 1 by A1 F12, 1 minus epsilon 2 by A2 epsilon 2. So this is the formula. Because this one, you know, this one EB1 is nothing but sigma T1 to the power of 4. So this is based upon the Stephen Boltzmann law. Total emissive power is equal to sigma into T1 to the power of 4. Similarly, EB2 is equal to sigma T2 to the power of 4. So T1 is the temperature of the first plate or first surface. T2 is the temperature of the second surface. Okay. So then the formula is sigma is the common term. You can take common, and sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 minus epsilon 1 by A1 epsilon 1, 1 by A1 F12, 1 minus epsilon 2 by A2 epsilon 2. So this is the formula. So by using this formula, we can see, we can derive the rate of heat transfer formulas, derivations with respect to different types of surfaces. So the first one we'll see here, between two parallel plates, we'll see between a small body in a big enclosure, we'll see this condition also. Two infinitely plates, next to between two plates one more shield is there. So we'll see all these conditions and we'll derive the formulas for those conditions also, for those plates, heat exchange between those plates. Okay, so next, first condition, a small body in a big enclosure. Okay, so big enclosure means so that one is very big compared to, so this body one. So body one, area of the body one is equal to A1, emissivity of the body one epsilon 1, and temperature of the body one T1. Okay, so it is surrounded by atmosphere. Suppose atmosphere means very big, then area, you can consider area as infinity. Okay, so in this condition, we'll take the we'll derive the heat transfer between these two surfaces, small body to big enclosure. So this is the formula. First we'll see, you know that basic formula. What is that one? Heat transfer, radiation, heat energy between two plates. So that is nothing but 1 minus epsilon 1 by epsilon 1. Okay, so 1 by A1 F12, 1 minus epsilon 2 by epsilon 2 A1. Okay, you can rewrite formula like this one also. Sigma, just we are taking A1, so as common term, or just we can multiply this one. This is not A1. If you multiply this one A1 by A1, so here A1, here A1 will be cancelled. What is this one? Not this one. So if you multiply this one, A1 by A1. Okay. So here, just like sigma A1 into T1 to the power of 4 minus T to the power of 4 by, here 1 minus epsilon 1 into A1 by A1 into epsilon 1 plus 1 by A1 F12 into A1. So just I am dividing 1 minus epsilon 2 by epsilon 2 into A1 by A2. Okay, so this A1 will be cancelled, this A1 will be cancelled. So finally we will get this formula. Okay, so the formula is equal to Q12 between any two plates. So just I am taking this formula. So sigma A1 by, okay, sigma A1 by, so these are the epsilons, don't confuse, these are the 1 minus epsilon 1 by epsilon 1. So 1 by F12, 1 minus epsilon 2 by epsilon 2 into A1 by A2. So this is the formula. But here, you know the condition. So that condition is equal to A2 is infinity. A2 is equal to infinity. So then this total term will be 0. Okay. So will be 0. So next to, then you can simplify this one. 1 minus 1 by epsilon 1. You can rewrite like this: sigma A1 into T1 to the power of 4 minus T to the power of 4 by. So 1 by epsilon 1 minus epsilon 1 by epsilon 1 plus 1 by F12. So in this case, so already discussed this one. F12 is equal to 1. So 1 by 1. So here 1 by 1. So minus 1 plus 1 will be cancelled. This is the 1 by epsilon 1. Then the final formula is like this one. The final formula is equal to epsilon 1 comes to numerator portion, sigma A1 epsilon 1 into T1 to the power of 4 minus T to the power of 4. So this is the formula for the rate of heat transfer between a small body in a big enclosure. Then you have to remember this formula, okay, to find these type of numericals. Okay. So next one, so this is the final formula. So next we will see two infinite parallel planes. Infinite parallel planes means you can consider both the areas are equal. Okay, so same. This is the condition. Same here also you can take the same formula 1 minus epsilon 1 by epsilon 1 f1 1 by f12 1 minus epsilon 2 by epsilon 2 a1 by a2. So both are same. This will be cancelled. Then area will be a1 is equal to a. Okay. So then the formula is equal to same here also. Okay. So f12 f12, what is the value of f12 for the planes? So for the f12 is equal to 0. 0. Sorry. Okay. Plane surface. It releases, but it does not comes to back. So it releases, it does not come to back means FO 11 and F22. So these are equal to 0, but F12 is equal to 1. So because we know that F11 plus F12 is equal to 1. So this will be 0 means F12 is equal to 1. Summation 2. Okay. So based upon this one, F12 is equal to value 1. So here this is 1 A by A. So then you can simplify this one. It means 1 by epsilon 1 minus epsilon 1 by epsilon 1 plus 1 by epsilon 2 minus epsilon 2 by epsilon 2. Okay. So this is value 1 minus 1 plus 1 will be cancelled. Here 1 by epsilon 2 by epsilon 2, that is the 1. The finally sigma A T1 to the power of 4 minus T2 to the power of 4 by, so the formula is equal to 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is the formula. So if the heat exchange by radiation between the two infinite planes, infinite plates means area will be same. Okay, area of both the plates are same because infinite we cannot measure the area. We can consider area of both plates are same. Okay, so this is the final formula. Sigma A into T1 to the power of 4 minus T2 to the power of 4 into A by 1 by epsilon 1, 1 by epsilon 2 minus 1. So by using this formula, you can solve the numericals. Numericals we'll see in next class. Okay. So next condition is the radiation shield. So placing of one shield in between the two plates. So to reduce the heat flow, it means to increase the resistance. We'll see what is the importance of radiation shield. Radiation heat transfer between two surfaces. It can be reduced greatly by inserting a thin or high reflectivity sheet. Okay. The main advantage of the placing of a shield is to reduce the heat transfer rate. It means increasing the resistance. Okay. So such highly reflective thin plates or shells are simply called as radiation shields. So shields means opposing the radiation process, heat transfer process, opposes the heat transfer process. So multi-layer radiation shields constructed about nearly 20 sheets per centimeter thickness. So you can understand the thickness of shields. Okay. So by evaluating the space are commonly used in the cryogenic and the space applications mainly. Okay. The radiation shield reduces the radiation heat transfer by effectively increasing the surface resistance. Okay. By increasing the surface resistance, automatically radiation between the two surfaces will be decreased. The lower emissivity of the shield that shows the higher resistance. Okay, so we'll see one condition. So this is the two plates are there. Emissivity of the first plate, emissivity epsilon 1, epsilon 2. Shield emissivity is equal to epsilon 3. Okay. Next, rate of heat transfer between the plate 1 to 3, next to 3 to 2. Okay. You can see this is the electrical analog formula for the this setup. Here, first EB1, emissive power of the first surface, then surface resistance of the first plate, that is the 1 minus epsilon 1 by A1 epsilon 1. You know this one. Then next to radiosity. Okay. So this is for first surface. Next we'll see space between the first plate and radiation shield. So we have to consider the resistance of the space resistance. That is nothing but 1 by A1 F13. So next to J3. So J3 means next because of this resistance we will get the radiosity of shield. Otherwise, for the shield, the shield also has the surface resistance, that is 1 minus epsilon 3 by A3 epsilon 3. Okay, so this is EB, next to resistance, next to radiosity. So the surface resistance between the J1 and J3 is 1 by A1 F13. Similarly, radiation emitting energy of the surface 2, next to surface resistance of the surface 2, next to radiosity. Next here also same conditional. So J3. So it means surface resistance of the this one shield A3 and here also A3. So these two terms are equal. Next EB3 is the emitting energy. So this is the resistance with respect to plate 2. This is the resistance of the shield with respect to B1. Okay, so this is the electrical analog formula. By using this formula, we can write the rate of heat transfer. So this is the formula for without radiation, without shield. So this is the electrical analog formula for the with adding the shield. Okay. So now we'll see if we place any shield between two plates, then what is the rate of heat transfer formula? We'll derive this one also. We know this one. If there are two plates, then rate of heat transfer F12 is equal to sigma A. If you consider these two plates are infinite parallel plates, sigma A, T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the formula. Okay. So here also we will use this formula. Suppose heat transfer between plate 1 and shield 3. It means rate of heat transfer from plate 1 to 3. So sigma A is area. So area of this plate and shield and this. So both are same. Okay. So all are same. So sigma A into T1 to the power of 4 minus T3 to the power of 4 because temperature of the shield is T3. Okay. So 1 by epsilon 1 plus 1 by epsilon 3 minus 1. This is the formula. Similarly, Q3 to 2. So shield to surface 2. So 3 to 2. So here also sigma A T1 to the power of 3 to 3 T3 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So this is epsilon 3 epsilon. We can combine this one. Okay, so next heat transfer between the surface 1 to surface 3. Okay, so just that is the EB1 minus EB2 by total resistances. What are the resistances here? 1 by epsilon 1 plus 1 by epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay, so this is the formula. You can see like this one here, just like so. This is epsilon 1, epsilon 3, epsilon 3, and epsilon 2 minus 1. So this is the formula. By using this formula, you can solve the numericals. So this is the formula when we place the shield between the two plates. So this is the formula for without shield. We can use these formulas. Okay. So this is the condition. We already discussed this one. So this is the one more condition. If the emissivities are same, epsilon 1 is equal to epsilon 2 is equal to epsilon 3 and epsilon. So the formulas will be like this one: 2 by epsilon minus 1, 2 by epsilon minus 1, then 2 by epsilon minus 1 into n plus 1. N shows the number of shields. Okay. The n is equal to 1, that is 2. N is equal to 2, that is 3. Okay. So that is the source. So this is the Q12 with shield. This is the formula. Q12 without shield. This is the formula. Okay. If the emissivity are equal. Okay. Emissivities are equal emissivity and areas also both are equal. So this is the formula. Q12 without by Q12. So this is the formula is equal to 1 by n plus 1. Okay. Number of n is the number of shields. So it shows the number of surface resistances and number of space resistances for the formula. Okay. So 2n plus 2. This is the number of surface resistances based upon the shields, number of shields. So this is the formula for the n plus 1 number of shield. What is the space resistances? Okay. So you can use these formulas. Okay. So these are the different textbooks I have given. You can so you can refer these textbooks to understand the concept of radiation between the plates, gray plates. Okay. So thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.